Hello and welcome to this video about graphing piecewise defined functions. In a previous video, we defined a piecewise function to be a function whose formula consists of at least two different formulas in such a way that which formula applies depends on where the input falls in the domain. As long as we are careful to make sure that each potential input has one and only one corresponding output, we can define a piecewise function using as many different functions on different intervals as we desire. In this video, we'll practice sketching an accurate graph of a piecewise defined function. Sketch an accurate graph of y equals w of t, which equals 1/3 t plus 4 minus 2 on the domain t less than or equal to -1, and -1/2 t minus 1 squared plus 3 on the domain t greater than -1. First, notice that the function w is made up of two pieces, a linear piece when t is less than or equal to -1, and a quadratic piece when t is greater than -1. We'll start by graphing the linear piece first. We notice that this linear piece is written in point slope form, so the line goes through -4, -2, and has a slope of 1/3. So from that point, we can go up 1 and to the right 3. And that does put us at a t value of -1, which is fine because -1 is in the domain for that linear piece. So we'll have a closed point there, and then we can draw our line between those 2 points. And we're finished graphing the linear piece. So to continue, let's tackle the quadratic piece of the function. We know the quadratic is written in vertex form. So the vertex is located at 1, 3. And we also know the parabola is concave down because a, -1/2, is less than 0. In order to sketch an accurate graph, we need to identify a few more key points on the graph of the quadratic piece. So first, let's see what happens near t equals -1 on the quadratic piece. Although the quadratic piece is not defined at t equals -1, we're still going to let t equal -1 just so we can see where the y values are tending towards near t equals -1 on that quadratic piece. So that would give us -1/2 times -1 minus 1 squared plus 3, and that simplifies to equal 1. So we substituted in -1, we got 1 out. So we know at -1, the quadratic piece is getting close to a y value of 1. So we're going to use an open circle there because technically t is only greater than -1 for the quadratic piece. Now let's find the y-intercept by evaluating w of 0. So 0 is greater than -1, which means it's appropriate to use the quadratic piece of this function. And when we let t equal 0, we get 2.5. So the y-intercept is 0, 2.5, and we can plot that on the graph approximately. And then let's go on and let's find the t-intercepts for the graph of the quadratic piece. And again, we know the quadratic's going to open down, so we know that somewhere, maybe around here, the graph is going to have to cross through the t-axis. All right, so we're going to let -1/2 t minus 1 squared plus 3 equals 0, and we can subtract 3 from both sides. We can multiply both sides by -2, and that will result in t minus 1 quantity squared equals 6. We'll take the square root of both sides, so t minus 1 equals plus or minus the square root of 6, and then we'll add 1, so t equals 1 plus or minus the square root of 6. And we are only interested in the t-intercept where t is greater than or equal to -1. So we're interested in t equals 1 plus the square root of 6. And if you use your calculator or technology, you'll see that's approximately 3.449. So our t-intercept is at 0, 3.449. We can estimate that on the graph. That would be right about here. And then if we wanted to use a little bit of symmetry to finish out this sketch, we see that from the vertex, when we go left 1 unit, we go down 1/2. So we could also go right 1 unit and down 1/2. When we go left 2 units from the vertex, we go down 2. So when we go right 2 units from the vertex, we would also go down 2. And then here is the sketch of, the quadratic piece of our function. So in conclusion, we were able to graph a piecewise defined function by graphing each piece individually on its defined domain. We used our knowledge of transformations and finding key points of a graph to help us sketch an accurate graph.